The first example that we'll look at is a punctured tire. You run over a nail. As the air leaks out of your tire, the rate of change of air pressure inside the tire is directly proportional to that pressure. This means that the rate of change of the pressure, dP dt, is proportional, so K, times P, to the pressure. Now, the first thing we'd like to do is write a differential equation that states that fact if the pressure, right, so here's our fixed values, the pressure is equal to 35 pounds per square inch, and is decreasing at a rate of 0.28 pounds per square inch per minute. So we know that if the pressure is 35 pounds, then the rate is 0.28. So what would our differential equation be? Well, what we know is that when dP dt is 0.28, then K, that will be equal to whatever the constant is, times 35. And this means that if we divide both sides by 35, we can solve for K. In this case, K equals 0.008. So our initial differential equation is that dP dt equals 0.008 times P. And since we're told it's decreasing, then that means that the rate of change was negative, so we should get negative 0.008. So there's our initial differential equation. Now we could go through our whole process of separating the variables, but we should know what's going to happen. We should know that if we solve this, we're going to end up with P equals some constant, C, times e to the k, which in this case is 0.008 times t. Right? We should know and have memorized that that's going to happen. Well, the question might be, well, what is C? Well, recall we were told that if the pressure is 35, then the rate is 0.28. So when our whole process started, the pressure is 35. That's why in this context, given our information, we know what what C has to be. It is 35, because that's the pressure that the whole process was starting at. Now, the next question could be, what's the pressure when T equals 10? Right, or 10 minutes after the entire process starts? Well, we've got our equation, so we'll just substitute in 10 for T and figure out what 35 times e to the power of negative 0.008 times 10 is. And it ends up being about 32.309. And remember that that's pounds per square inch. D. The car is safe to drive as long as the pressure is 12 pounds per square inch or greater. How long after the puncture will the car be safe to drive? So what we know is the car is good when the pressure is 12 or greater. Let's see, it is 12 at this point. We need to solve for T. let's solve for t. First, I'm going to divide both sides by 35. So I'll have 12/35 equals e to the negative 0.008 t. And this is in exponential form, so I'm going to convert it to log form. So this is the natural log of 12/35 must equal negative 0.008 times t, which means that t must be equal to exactly the natural log of 12/35 divided by negative 0.008, which means that t is about 133.805, and that's minutes. 805 minutes. So this score will be good for at least 2 hours. Let's look at a second example problem. Here we have an instance where there's bacteria in a lab culture, and it's growing in such a way that the instantaneous rate of change of bacteria is directly proportional to the number of bacteria present. So that tells us that the rate dB dt, the rate of change of the bacteria, is equal to K times B. If we were to solve this differential equation, we could go through our process of separating the variables, or we can have memorized that this will become B will be equal to some constant, which will be the starting amount of bacteria, times E to the K times T. Suppose that initially there are 5 million bacteria. So we know when t equals 0, there are 5 million bacteria. And 3 hours later, so when t equals 3, there are now 7 million bacteria. So I'm going to let B represent the number of millions of bacteria that exist. And I know that when we start, there's 5 million. So I immediately know that part of my equation is that B equals 5 e to the kt. Because when this whole process starts out, there's 5 million bacteria. The problem is I don't know what k is, but I can figure it out because I know that B is 7 when t is 3. And now I can solve for k. I'm going to divide by 5, so this will be 7/5 equals e to the 3k. I'll convert this to logarithmic form, so we'll have the natural log of 7/5 equals 3k, and k is exactly this value, the natural log of 7/5 over 3. And so I'm going to keep using k in my work, but when I actually have to calculate at the end, I'll use this number, so I'm not going to round now. So this is my particular equation here, and I've solved for k. Sketch the graph of time versus bacteria over 10 hours. Well, if we were just to sketch the graph of our equation, what's going to happen is when t equals 0, I'll be at 5, and when t equals 3, I'll be at 7 million. But it's just going to keep growing more and more and more. And notice that the slope of this line is getting steeper and steeper and steeper, and that should make sense, right? It's the rate of change is proportional to the amount that's there. What will the bacteria population be 1 full day after the first measurement? Well, this is asking what will we have when t equals 24? So how much bacteria will there be when t has a value of 24. And remember, I know what my value k is, so now I'm just going to calculate this. I get that there are 73.789, this is million bacteria. 73,789,000 bacteria is how much there would be in a day. And the last question is, when will the population reach 1 billion? So I want to know, when will there be 1,000 million bacteria, or 1 billion? So when does 1,000 equal 5 e to the k t? K still has this value that we solved for. So first I'm going to divide by 5. So 1,000 divided by 5 is 200. I'm going to convert this to logarithmic form. So the natural log of 200 equals kt divided by k. So the natural log of 200 divided by k equals t. So t is about 47.240 hours. So there we have 2 example problems on dealing with exponential growth.